Organizers, it's a very good opportunity given to me to start this conference. First of all, let me congratulate WCOC organizers for successfully conducting this platform and giving organic chemists this platform so that they can interact with each other and their ideas can be shared. Thank you so much for giving this opportunity to all the organizers, and my regards to all esteemed audience. So I'm going to start.
Good afternoon, ladies and gentlemen. My name is Sylwia Sowa, and I'm working as Associate Professor at Department of Organic Chemistry and Crystallochemistry at Faculty of Chemistry at Maria Curie-Sklodowska University in Lublin. And the topic of my research is the synthesis of 3-aryl benzophosphole oxides, the compounds that has been recognized as a new building blocks in benzophosphole family. Benzophospholes are, I'm here. Yes? Everything is okay?
Yes, please continue.
Okay, the benzophospholes are non-aromatic heterocyclics with enhanced conjugation in the unsaturated bond system. It was proved that their conjugation can be tuned through the substitution at the 2 and 3 position. Therefore, the benzophosphole family can be classified according to the substitution. And here, the model representatives of each groups are given with their reported applications. These include unsubstituted, 2 substituted, 3 and 2 and 3 substituted benzophosphole oxides, as well as molecules structures possessing 2 molecules of benzophosphole oxides, as well as benzodiphosphole oxides, more conjugated. Among them, 3 substituted benzophosphole oxides are the most recently discovered members of benzophosphole family. It was not until 2018 that the first patent for 3-aryl benzophosphole oxide synthesis was filed. 3-ortho phenyl benzophosphole oxide was obtained through Suzuki-Miyaura reaction using 3-bromo benzophosphole oxide. The major limitation of this method is the limited access to 3-bromo benzophosphole oxide, which is a minor product from the reactor-to-step process reported by NIF. Lately, 3-phenyl benzophosphole oxide was obtained by a double PC bond formation. Soon later, the scope of double PC formation approach was broadened, and the employment of the substituted aryl phosphinic acid and substituted diphenyl ethylenes was broadened, and the new library of 3-aryl benzophosphole oxides was obtained. However, this method provides a convenient access to those compounds. Its limitation is that when we have the symmetrical substitution in parent alkene, we end with the substitution at both para position in aryl phenyl introducing at the 3 position, and also with the same substituent at the 6 position in benzophosphole oxide. Why are the 3-aryl benzophosphole oxides gaining more attention among chemists? The answer lies in their potential applications. Recently, Miyaura and Hirano have successfully used 3-aryl benzophosphole oxides in their coupling with aryl iodides and bromides to obtain unsymmetrical 2,3-diaryl substituted benzophosphole oxides. This reaction is based on the CH activation of this bond here, and can be also carried out with other compounds, and here we see the double CH activation in benzophosphole and also with alkene, and also the reaction can be done with alkanes. Alkanes and alkenes. The same group has successfully functionalized the benzophosphole core at the 2 position with alkoxymethyl groups, like you can see here, with a phosphoryl group, like here, and also with alkoxycarbonyl group, like we can see here, with all reactions with very good results. So these protocols prove that 3-aryl benzo-biphosphole oxides are valuable building blocks in the preparation of unsymmetrical 2,3-desubstituted benzophosphole oxides. From the synthetic perspective, there is a constant demand in the synthesis of 3-aryl benzophosphole oxides, which can be then used as a building blocks. To access a new library of 3-benzyl phosphol oxides, we considered a retrosynthetic pathway which starts with the disconnection of C-aryl bond, which lead us not to a bromide like before, but to a triflate, which can be now obtained from the corresponding benzophospholan trion, this cyclic ketone, we can say, and this ketone can be obtained from the tertiary phosphinoxide, which possess methyl group and alkoxy-carbonyl phenyl substituent. The final step leads us to the secondary phosphinoxide and aryl iodide. To obtain regioselectively substituted products, we suggested to use the substituted aryl iodides, which allows to functionalize regioselectively the cyclic triflates in the subsequent reaction. And at the end, we can add the final substituent according to the conditions of Suzuki-Miyawara reaction. According to our plan, we started the synthesis of the triflates from the beginning, starting from the secondary phosphinoxide, which was subjected to the Ullmann coupling with this aryl iodide. From the first step, we get the tertiary phosphinoxide 1, which was then subjected to the reaction with strong base LDA, and we obtained the ketone 2. This ketone was subjected to the reaction with sodium hydride, which provides enolate, which then is esterificated in the presence of triflic agents, providing the triflates. All the processes were successful, and we obtained the substituted and unsubstituted triflates with good yields. Having the triflates in hand, we optimize conditions for the model reaction of triflate 3A. Sorry, here's supposed to be 3 and 3A, and with phenyl boronic acid 4A. It seems that palladium tetrakis triphenylphosphine, sorry. it's the best is the best catalyst for this reaction, and we can see all the reactions here. This catalyst is compatible with the most of the solvents used, so this DMF, THF, toluene, dioxane, and DME. And in most of these reactions, we get isolated yields from satisfactory, or say moderate to good. However, in the reaction which was carried out below the solvent boiling point, a significant amount of unreacted triflate was still present or recovered after the reaction. The reaction carried out in sealed tube at 110 degrees Celsius were working better, but the best of this reaction was the reaction in this table entry 9, which provided most pure product, which didn't contain a lot of aromatic byproducts, which probably arise from the polymerization of boronic acid. In this case, we also didn't observe too much of triphenylphosphine, which arises from the decomposition of the catalyst. And finally, we obtained the expected product with very good yield, 88%. So those conditions was the best. However, we also checked the other base, the sodium carbonate in solution, and this base also worked with the same condition as the best conditions. However, the yield was better, and also we have checked the addition on lithium chloride, which was suggested by the literature, and this addition didn't improve the yield of this another catalytic system. Finally, the other catalytic system based on the other catalyst, palladium catalyst, didn't work very good. We can say their performance was rather poor. Having the optimized conditions in hand, we subjected the model triflate 3A to the reaction with a variety of substituted boronic acid under the best conditions to get the variety of phosphine oxides, 3-aryl phosphine oxides 5. As we can see, using this protocol, we can achieve complete conversion of triflate 3A for boronic acid, which have with electron withdrawing groups like halogens and nitro groups, and also for electrodonating groups like methyl, methoxy, hydroxyl, and amino. 3-aryl benzophosphole oxides possessing para-substitution in 3-aryl ring, and also those possessing meta-substituted were obtained in yields ranging from 83 to 99%, except for the amino substituted, because here we have the decrease of the yield, which is caused by the interaction with acidic silica gel during the purification. This is the reason that the yield probably is getting worse. Unfortunately, when we go to the parachlorosubstituted or the other benzophospholes, which are derived from the boronic acid with meta and ortho substitution, the purification was difficult and impeded by the presence of triphenylphosphine oxide. Triphenylphosphine oxide we were unable to remove it after one single column, and the yields were calculated for these compounds according to proton NMR. However, the amount of this triphenylphosphine oxide in the mixture with the product was about 5 to 10%, but it needs some improvement for the purification of this compound. Then we go to scope of the reaction. I don't know how to remove this stopping for that. Then with optimized conditions, we now examine how the substituent R1 in the triflates impact the reaction course, and we have found that the reaction similarly to triflate 3A, which was unsubstituted, the substituted triflate 3B, C, and 3 and D, despite of regardless of the type of substitution. So we can name it electron donating, like methyl groups, and methoxy group was providing the expected products 6 and 8 with very good yields. Also, the triflate possessing the chloro substituent also provided the products, however, in quite a bit lower yield due to the problems with the purification. It was also found that the reaction is scalable to 1 millimole, and in this case, the use of triflate 3B with methyl substitution, we obtain in reaction with nitro phenyl boronic acid product 6N with yield 91%, and as and we, when we go further, unfortunately, the situation is happening again, that we found the products also substituted with methyl group and methoxy group that are quite difficult to separate from the byproducts 3-phenylphosphine oxide. And in this case, we unfortunately have to calculate the yields according to proton NMR. Once again, this amount of 3-phenylphosphine oxide was quite low. However, they are not enough pure. I don't know what to do with that. Sorry. Oh, maybe not. 14. Having a library of pure 3-aryl benzophosphole oxides, we have we decided to test their fluorescent and optical, and generally optical properties, and the usual method for that are theoretical and spectroscopic methods. But first, we check this literature, and literature survey shows that previously reported benzophosphole oxides with different type of substitution provided a wide range of fluorescent properties, from weak to very good. And we can describe classify them into two groups. First, which derive their fluorescence from the conjugation, and in this group, the impact of the substituent at the 3 position is quite disappointing, because here this substituent is responsible for the decrease in the fluorescent properties with very, very poor fluorescence, quantum fluorescent yields. However, in the second group, in which the fluorescent origin is different and is derived from the internal charge transfer in the molecule, the presence of the substituents at the 3 position contributed to the fluorescence increase, and here the fluorescence is very high. So we ask what type of fluorescence belong our 3-aryl benzophosphole oxides, and they have never been studied before, so it was worthy. And first, we have examined the properties of selected 3-aryl benzophosphole oxides according to using the DFT calculation analysis of HOMO and LUMO levels for those compounds allow us to see the origin of the fluorescent properties. For this study, we selected 3 different benzophospholes possessing phenyl, hydroxyphenyl, and metanitrophenyl group. For 5A and 5H, their electron density maps are determined tightly by the benzophosphole ring. So this part of the compound deciding the properties of this compound, and the only difference between 5A and substituted 5H is the impact of the hydroxyphenyl substituent on the HOMO level here. In case of 5N, which possess a nitro substituent, we can see the separation of the HOMO-LUMO levels. Generally, they are not the same. They are completely separated, and also here, compared to this previous ones, nitrophenyl ring determines the LUMO level instead of benzophosphole ring, and here also the benzophosphole ring in HOMO level is responsible for benzophosphole ring is responsible for the HOMO level. Here we can say that these 2 types of compounds have different we already see that these 2 pairs of compounds have different properties, but we have to check more. So to better understand the differences in the properties of the selected compounds, we studied their geometries in ground state and excited state. And figure 1 shows all the geometries with the structure of the compound. And at the beginning, we have compared the torsion angles for all the compounds at the beginning. So the torsion angles for 5A and 5H are in ground state equals around -50 degrees, and we can say that the aryl ring connected to the benzophosphole is in the twisted fashion. So it's not plain. It's rotating. So when we go from the ground state to excited state, this aryl ring become more planar, not completely, but more planar, and this indicates the increased conjugation in the excited state. In case of 5N, this torsion angles equals is in the different the rotations in the different or have different this ring has different orientation, and the torsion angle is around 33 degrees and is decreased slightly in the excited state. We can also we have also checked the torsion angle from the X-ray structure, and this X-ray structure and the ground states have similar values of torsion angle. The comparison, the geometry was also supported by the comparison of dipole moments of ground state and excited state for 5A and 5H. The both states have the similar values of the dipole moments, while for 5H we possess 5N possessing nitro substituent, we observe a significant increase in the excited state, which means that excited state for 5H is highly polarizable. This also indicates the differences in the optical properties for these two compounds and 5N, which behave quite differently. Most of the data from this previous geometric study was collected in the table 3, and this table shows the bond lengths and millikan charges related to the conjugated bond system. In bar chart 1, I have visualized the bond lengths from this unsaturated bond system, and as we can see, the double bonds O1 P1 and C2 C3 are elongated for 5A when we are changing from S0 to S1, as well for 5H when we are changing from S0 S1. Both the same double bonds are increased. Instead, in contrast, the single bond pH P1 C2 is shortened. When we go to compound 5N, the elongation of only the one double bond is significant, in contrast to these two previous compounds. When we speak about the charges in the conjugated bond system, ground in excited states, for 5A and 5H, the charge in the ground state is quite low, but when we go to the excited state S1, this amount of charge is growing in the unsaturated bond system. So the both states are differ in the amount of the charge between these two states. In contrast, for 5N, which possess the nitro substituent, the differences between both states are minimal. So we can, from this point, see that the geometry is not the origin of the properties of 5N. In contrast, for 5A and 5H, the conjugation, the conjugation is the origin of its properties, and the geometry is quite affected in their cases. Then we go to the spectroscopic data, and we tested all optical properties for each compound separately. For 5A, so the 3-phenyl benzophosphole oxides, changes in absorption band in polar solvent are subtle, between 316 and 320, but in less much polar toluene, the abatochromic shift of absorption band is observed to 322-25. The emissive properties of 3-phenyl benzophosphole oxide 5A are not exhibit strong solvent dependence, so we can see the very similar emission bands values, as well as similar not very growing values of stock shifts. So this compound is not very dependent on the solvent polarity. So it's quite consistent with the spectroscopic data, where we define that this compound originates the fluorescence from the benzophosphole ring, and this means that the medium polarity of the medium doesn't affect it too much. And we can say also that it's very weak fluorophore with a highest value of fluorescent quantum yield equals 0.7% in the DMSO. And then we see the decreasing due to the non-radiative dissipation. When we go to hydroxyphenyl benzophosphole oxide, we can see that the absorption spectra is more structured, especially in polar solvents. In toluene, we also have only one emission band. When we go to the fluorescence study, 5H exhibit the highest fluorescence in low polarity solvent toluene, with the highest value of fluorescent quantum yield equals 1.74%, and the lowest value of emission band 414 nanometers. This compound is also, when we go to the more polar solvent, the shift of the emission bands is visible, is bathochromic shift, but the fluorescent quantum yields are decreasing because of the non-radiative decay. So we of non-radiative emissions. We can be confused because this compound also belongs to the group that doesn't not supposed to be affected by the solvent, and here we see the change in the emission bands. However, this change is not originating from the solvent dependence, which the proof for that is the quite tight stock shift range, which suggests that this compound still is in the group of fluorescence originating from the conjugation. But when we change the interaction from toluene, which prefer the pp stacking interaction, to the polar solvents, which prefer the hydrogen bonds interaction, this affects the fluorescence, and we can also here see that the fluorescence is quite complex phenomena that can be affected by different factors, and we have to check all. And we also supported the experimental data with the calculation of electronic transition, and we can see that absorption of the parahydroxyphenyl benzophosphole oxides can have two electronic transition for the absorption, which are related with those levels, and they are supported with the energy differentiation in polar solvent, and in non-polar solvent the ground energy is lowered, and this results in the only one transition. When it comes to the nitro substituted phenyl ring, it also is have a very similar profile in absorption like 5A, and has very only the one is only fluorescent in toluene with very high value of stock shifts, which means that this compound is very different from these two previous ones, and its fluorescence is affected by the solvent polarity, which is the proof, the very high value of the stock shifts even in toluene. Also, the proof is that this fluorescence is very decreased. Even we can say that it's not fluorescent at all in the very polar solvents. It means that this the non-radiative dissipation is very preferred in polar solvents for these compounds, or we can say that this nitro group is causing the quenching of the fluorescence, and this is the reason for those results. And at the end, I have the comparison of all the data collected for the best solvents like THF and toluene. And here is the fluorescence spectra in THF when we have shown comparison. So the best fluorescent compound, blast fluorophore in this selection is parahydroxyphenyl compound, which has the highest value of fluorescent quantum yields in both solvents, as well as have very have the shifted emission band here. Here is quite not. However, we can see also that those two compounds, 5A and 5H, differ from the 5N, which have very high value of stock shifts, and those have very similar values. Doesn't matter if we are in polar solvent or in more non-polar solvent. So at the end, I want to just summary that we have developed a new road to a new library of 3-aryl benzophosphole oxides. We have obtained a library of these compounds in which the substituents in benzoring and at the 3 position are independently introduced, what was very difficult before, and we have shown the relationships between the structure and the optical properties of these compounds, and we have proved that substitution at the 3 position has impact on the fluorescent properties of the benzophosphole oxides. So we can also say that knowledge that we gain in this study can also be used to plan new compounds in more rational way. At the end, I want to thank my all co-workers for the help in the optimization of the result, my student for the fluorescence study, for all these three girls, like Dr. Agnieszka Lipke and Dr. Agnieszka Gładysz-Płaska and Dr. Monika Zubik-Duda. We also want to thank for DFT calculation for Dr. Agnieszka Brzyska and for the X-ray analysis Dr. habilitowany Łukasz Ponikiewski, professor from Gdańsk University of Technology. And I want to thank you for your kind attention and the possibility to share this talk with you and to share my data with you. And I want to invite you to our city, Lublin. And I'm waiting for your question if you want to ask.